we have discussed in very detail the basic theory of time-dependent perturbation theory. In fact, in the basic concept of time-dependent perturbation theory, first of all, we have obtained the general result for the transition probability. That is, the probability of transition of a system from one perturbed state, or you can say initial perturbed state, to transit into the another unperturbed state. Okay. Actually, the result which we have obtained in general form for getting that transition probability, in principle, that result can be used to calculate the transition probability to any order. But I have told you that the terms higher than the first order become rapidly intractable. And for most problems of atomic and nuclear physics, only the first order transition probability is sufficient to get the correct result. So now we will discuss actually the two situations for finding the transition probability. In first situation, which we will discuss in this present lecture, we will find the transition probability for a constant perturbation. When you say constant perturbation, that means the perturbation which is independent of time. Okay. And after that, in second lecture, we will see the calculation of same transition probability, but in case of a harmonic perturbation or periodic perturbation. But in these two problems, we will talk about the calculation of transition probability only to the first order. Okay? Because I have told you that this first order transition probability calculation is sufficient to get the accurate result. So, as I have told you that our present concern is to find the transition probability for a constant perturbation. Actually, at the end of the lecture, you will see we will obtain a very important rule which is called Fermi golden rule. And in your examination, particularly in short answer type question, this Fermi golden rule is asked to you separately. So the step which I will follow to obtain this Fermi golden rule, you have to write the answer of that very question only in that steps. Okay. So let us start to know about the calculation of transition probability for a constant perturbation, that is time independent perturbation. Okay. And for this we will need the previous result which we have obtained in my previous lecture for the first order transition probability. We have seen the first order transition probability for the transition of a state ket psi I to ket psi f when I is not equal to f. Both are different states, but this ket psi I is the unperturbed state and ket psi f is another unperturbed state. So when a system passes from the unperturbed state ket psi I to the another unperturbed state ket psi f, then what will be the first order transition probability we have obtained? So I have mentioned that result here directly. This is given by PIF of t equal to a square of the modulus of minus I over h bar times integral 0 to t the scalar product of V operated on psi I with psi f times e to the power I omega fit dt. Okay. You have to remember this result because when you will write the answer of a question for calculation of transition probability for a constant perturbation, then your starting equation will be this. and so you must remember it. Okay. In basic theory we have obtained this result, but for this particular problem you have to write down this expression for the transition probability directly, so you must remember it. Here this v hat of t, this is the time dependent perturbation. And what is this omega fi? Actually this is transition frequency. This is the frequency which our this is the frequency of the radiation which our system will either absorb or either emit during the transition. Okay. And this omega fi is given by ef minus ei over h bar. Here ef and ei, these are the expectation values of the final state of the system and in initial state of the system. And so instead of ef you can write this expression, because this ef is the expectation value of the unperturbed Hamiltonian h naught in the final state kth psi f. And similarly this expression represents the expectation value of the unperturbed Hamiltonian h naught in the initial state kth psi I. Okay. So this is omega fi. Now in fact when this v of t will be constant, it is independent of time, then what will be the value of this pif? Our aim is to calculate. This is the concern of this present lecture. Okay. So it is very easy, and you will see a concept of Dirac delta function will be needed to explain the result. So let us now first of all calculate this pif of t. Okay. If you consider that this perturbation v is not a function of time, it is not time dependent, but it is constant. It does not change with change in time. So in this condition, that expression for pif, minus I mod square, this will be simply equal to 1. Okay. And therefore this expression is written as 1 over h bar square, a square of the modulus of this quantity, that is v hat operated on kth psi I, and then you take the scalar product of it with psi f, times integral 0 to t e to the power I omega fit dt. In fact this quantity is time independent, so it is outside of the integral. Okay. Now let us simplify this result. This simplification is very easy, you can easily understand it. This is 1 over h bar square times this much square. Okay. And now the integral of e to the power I omega fit with respect to t will be what? This is e to the power I omega fit divided by I times omega fi. Okay. And the limits are 0 and t. Okay. Now let us substitute the limit. This factor is at it, you can see. And when we will substitute the limit, the first term will be e to the power I omega fi times t, and minus the lower limit is 0. So there will be e to the power 0, and e to the power 0 will be equal to 1. So here there will be minus 1. And again that modulus of 1 over I square, this will be again 1. Okay. So I have omitted this I from here. Okay. And only omega fi has been written. Now definitely you have an idea of Euler's formula in trigonometry, that the modulus of e to the power I theta minus 1 square, that is simply equal to 4 times of sine square theta by 2. So utilizing this very formula, you can write the expression for this e to the power I omega fit minus 1. Here at the place of theta, you can see there is in fact omega fi times t. Okay, omega fi times t. So when you will use this formula, this result will become like this: pif of t equal to 4 times of this quantity, which is just the scalar product of v operated on psi I with psi f square, and divided by h bar square omega fi square times sine square of omega fit divided by 2. Okay, I think this calculation was very simple, and definitely we have understand each and every step clearly. Okay, now in fact after getting this result, our aim is to explain this both by the graphical method, or you can say logically, and also in a quantitative manner. And for this actually I have plotted here this uh, probability transition probability function in against of omega fi. Here one thing you should remember, that this omega fi here has been treated as a quantity having continuous value. Although omega fi is quantized, but the values of the two consecutive values of omega fi will be so small, so the difference of the two consecutive values of omega fi will be so small, so that it may be assumed to have continuous values. So considering omega fi having continuous value, we have plotted the transition probability in against of it, and that plot has been actually shown here. I have not written here PIF of t, but instead of I have written this factor, because in except this factor in the expression of PIF of t, everything is constant. Okay, so variation will be in accordance with this sine square omega fit over 2 divided by omega fi square. Okay, in fact as a function of time, this transition probability you can see is an oscillating sinusoidal function with a period of 2 pi by omega fi. This is actually the period of this oscillation of the transition probability, because the presence of this sine square function, this will not have negative value, only positive value, but it will oscillate sinusoidally, but its amplitude does not remain constant. Okay, so as a function of omega fi, however you can see the transition probability how varies with omega fi, you can see in this figure. And if you have studied interference and diffraction in your course on optics, then remember what you have studied when you have discussed the diffraction or interference pattern in case of a single slit. In case of a single slit, the diffraction pattern is just as shown in this figure. The central maxima is very bright in that case, and the higher order maxima continuously decreases in its intensity. So this graph you can see just appears like an interference pattern, or you can say a diffraction pattern. Okay, actually the appreciable value of this transition probability is around this omega fi equal to almost equal to 0, because around omega fi equal to 0 you can see there is a high peak, but as the value of omega fi increases from this 0 either in positive side or in negative side, you can see in that condition the intensity, the value of the transition probability decreases continuously. The maximum value of the transition probability decreases continuously. You can see the first order, this is 0 order maxima, This is first order maxima, this is second order maxima, this is third order maxima. Similarly, in this negative side, these are the first, second and third order maxima, and the value of this maxima continuously decreases. Okay, so you can say that the value of this transition probability is appreciable only near omega fi is equal to almost equal to 0, and it decays rapidly as omega fi moves away from 0. Okay, and as I have told you that for a fixed time t, we have assumed that omega fi is a continuous function or continuous variable. That is, we have considered a continuum of final states. Okay, actually, as I have told you earlier, that we will deal with this continuum of final state in the end of my lecture, of the present lecture. Okay, so this means that the transition probability of finding the system in a state kate psi f. What will be the transition probability of the system of finding in this final state, which is denoted by the symbol kate psi f of energy EF? What will be the transition probability? You can see this is actually greatest only when EI is almost equal to EF. EI is almost equal to EF. Why? Because you know omega Fi is equal to EF minus EI divided by H bar, and the finding of the transition probability of the system in a state psi f is maximum, it is greatest when omega fi is almost equal to 0. So when omega fi will be almost 0, then EF minus EI will be almost 0, and so you can say that EF is almost equal to EI. Then actually the probability of finding of the system in its final state will be maximum. Okay. Now, one thing is very remarkable here, that the height of this central peak, this is its height. You can see here I have marked its height by t square by 4. So height, if you denote by the symbol h symbolically, then this is actually proportional to t square. On the other hand, the width of this central peak, if you denote it by the symbol b, this is just inversely proportional to t, because you can see at that at this value 2 pi by t, this is 0. Okay, again at 4 pi by t it is 0. So this width is inversely proportional to t. Okay, so this is a very remarkable fact, that height of this central peak is proportional to t square, and its width is proportional to 1 by t. Okay, so if you calculate the area under this central peak, this area in general, this, if you denote this area by a, then a is almost equal to hb, not exactly it, because it is not completely rectangular, but it will be of the order of hb, and so you can see h times b, this will be of the order of t, and therefore we can say that area of this central area under the central peak is directly proportional to t. And actually this area is the measure of this transition probability. So you can also say that this transition probability PIF is directly proportional to t. It means this transition probability will increase linearly with increase in time. Okay, so this is a very remarkable fact, that the transition probability therefore grows linearly with time. Okay, and with increase in time, you can see the height will increase but width will decrease. So how this uh, transition probability will appear? In fact, as the height increases, width decreases, okay, but area remains constant. Area remains constant. So this behavior is just like the behavior of a Dirac delta function. If you have studied Dirac delta function, then you will see that in case of Dirac delta function, such property is actually exhibited by it. All these facts I have mentioned here, which I have just explained. So again, for clarity, I will give a reading and again I will explain it. So I have mentioned here, you can see as a function of time, this transition probability is an oscillating sinusoidal function with a period of 2 pi over omega fi. And as a function of omega fi, however, the transition probability has a diffraction pattern, or you can also say interference pattern, because whenever a diffraction takes place, after diffraction the waves interfere, and it is appreciable only near omega fi is equal to 0, you have seen, and decreases rapidly as omega fi deviates from 0. Okay. Here, a fixed time omega fi has been treated as a continuous function. Okay, it means the transition probability of finding of a system in a state kit psi f of energy ef is maximum only when ei is almost equal to ef, or omega fi is equal to 0. Again, I have told you that the height of the main peak, or you can say central peak, centered around this omega fi equal to 0 is proportional to t square. So h is proportional to t square, and its width is proportional to 1 over t, that is b is inversely proportional to 1 over t. Okay, and therefore area, which will be roughly equal to h times b, because it will be exactly h times b only when the shape of the region under the curve will be rectangular, but this will be roughly h times b. And so area will be proportional to t squared times 1 by t, that is a is proportional to t. But as I have told you that this area under the central peak is the measure of the transition probability. So this transition, if area is proportional to t, that means the transition probability is proportional to t. It means the transition probability PIF increases linearly with time t. Okay. Now again, you have seen that h is proportional to t square. So with increase in time, height of the central maxima will increase. On the other hand, since width of the central peak is inversely proportional to time t, so with increase in time, its width decreases. Okay, and therefore you can see I have shown here that actually when time is t1, after a time t1, the graphical plot of this PIF, okay, in against of omega fi is like this. This first curve actually denotes the plot of PIF against omega fi at a time t1, and after some later time, after some time, when time increases and becomes t2, at that time the peak is appears like this. At time t3 it appears like this. Here you can see actually with increase in time, here I have considered t1 is less than t2 and this is less than t3. So with increase in time, what you are observing, the height of the central maxima or the main maxima actually increases On the other hand, its width decreases. But area under any curve will remain same because that area is the measure of this PIF and the PIF is constant. Okay. So when we consider that time will tend to infinity, then what this curve will appear, in which shape this curve will appear? This curve will appear just like a high spike which I have shown by this arrowhead. In fact, when t will tend to infinity, then width of this central maxima will tend to 0. On the other hand, its height will tend to infinity, but area will remain same. This is actually the behavior or the property of a Dirac delta function. Okay. So you can say that in the limit t tending towards infinity, the transition probability takes the shape of a delta function. Okay. So I think now it is very clear to you that when t will tend to infinity, our transition probability function PIF will be just like a Dirac delta function. Okay. Now this fact which we have actually explained here by argument, now we are going to see this explanation in an analytical way. And for this, as I have told you, you need a concrete idea of Dirac delta function. If you have not studied Dirac delta function, you can consult any textbook of physics, mathematical physics or quantum mechanics, where you will get a detailed discussion on this Dirac delta function. Actually, one of the very important properties of Dirac delta function is when like this, limit t tends to infinity sine square xt over pi x square times t is equal to delta x. You know, delta x is the Dirac delta function centered about or centered at x equal to 0. If it is centered at x equal to, let us say, x naught, then this is denoted by delta x minus x naught. It means this Dirac delta function is centered at x equal to x naught. And when you write the symbol delta of x, that means this is centered at x equal to 0. Okay. X equal to x naught. Okay. Or this result may be written as limit t tends to infinity sine square xt over x square. That will be simply pi times t times delta x. Okay. Now, in the expression of PIF of t, the time dependent factor is like this. This is 1 over 1 by 2 omega fi whole square sine square omega fi t over 2. This is a factor in PIF. This factor will actually decide what will be actually the nature of the function PIF when t tends to infinity. On the basis of that very result, you can write when t tends to infinity, this expression will be equal to this much. This is 2 pi t times h bar delta h bar omega fi, where you know this h bar times omega fi is equal to ef minus ei, because omega fi you know is ef minus ei over h bar. And so this delta h bar omega fi may be written as delta of ef minus ei, because h bar omega fi, you can see this is ef minus ei. So in this limiting condition, or you can say in the limit of long time when t tends to infinity, then what will be the transition probability, which we have actually written in your equation number 1. Okay, actually this result will now become PIF of t equal to, you can see this is 2 pi t over h bar times this much times delta of EF minus EA. Actually, except this factor, okay, uh, the remaining factor is this much, whose value is this. So when you will use this equation 2 in your result, which you have defined in equation 1 for PIF of t, then you will get this. So this is the final result for the transition probability after a long time when the system gets transit from initial state to final state, that is ket psi A state to ket psi F state. Then the transition probability is given by this result. For solving the numerical problem, you have to remember this result too. Okay. Now, after getting this result for transition probability, we can now easily find the rate of the transition rate. When you say transition rate, that means transition probability per unit time. In unit time, what will be the transition probability? So for getting the value of a transition rate or transition probability per unit time, you will have to divide this PIF of t by t. In time t, the transition probability is PIF of t, and so in unit time its value will be PIF of t divided by t. So when you will divide the equation 3 both sides by this t, then you will get actually the transition rate. And you can see in RHS this t will cancel out then, and therefore you can easily say that the transition rate, which I have denoted by the symbol gamma IF, this is capital gamma, that is equal to PIF of t divided by t, and that it will be equal to 2 pi over h bar times this much times delta of EF minus EA. Okay, so this is the expression for the transition rate, and you should also remember this result for solving the numerical problems or any application based on this time dependent perturbation theory. Now remember some of the properties of this Dirac delta function, or you can say the basic definition of Dirac delta function. You know, a Dirac delta function delta EF minus EI, this is infinity when EF is equal to EI, because in this condition this appears like a high spike. Okay, here EF is equal to EI, and here this delta function will tend to infinity. Okay, but as one moves from this point EF barabar EI, this delta function abruptly falls to 0. This is a very crucial point. So when EF is not equal to EI, delta function will be 0. So let us see. If EF is not equal to EI, then in equation 4, this delta function will be 0. And if delta function is 0, this transition rate will be 0. Okay? But this transition rate will be not 0, it will have a non-zero value only when EF is equal to EI. And if EF is equal to EI, that means energy remains conserved. The energy in initial state and energy in final state is same. It means this delta function, delta EF minus EI, guarantees the conservation of energy in the limit t tends to infinity. Because I have written here, this gamma IF will be not 0 if EI is equal to EF, but if EI is not equal to EF, this gamma IF will be 0. Okay. So what we are actually observing here, you can see this constant perturbation, that is the time independent perturbation, neither removes energy from the system nor supplies energy to it. Okay? Neither energy is extracted from the system in case of constant perturbation, nor energy is added to the system. So, since we neither extract energy from the system nor energy is added to the system, therefore, in this case, energy of the system remains constant, and that's why we have told you, I have told you that this delta function guarantees the conservation of energy. So it simply causes energy conserving transitions. So if an objective question is asked in case of constant perturbation, energy of the system remains conserved or not? Energy of the initial state and final state remains same or not? Answer will be yes. That will remain same. Okay. So this concept, I think, is now very clear to you. Now, after obtaining the expression for this gamma IF, that is the transition rate, now we are going to see transition into a continuum of final state. And as I have told you earlier, that when you talk about the transition into a continuum of final state, in fact, in that condition, we will find the total rate of transition, and that total rate of transition will be obtained considering that the energy of the system or the frequency of the transition has a continuous value, and the result obtained for the total transition rate will be called actually the Fermi golden rule. So what is this Fermi golden rule? How we can obtain it? Let us now see. So now I am talking about transition into a continuum of final states. Okay. So what will be actually the total transition rate when a system transits from an initial state, let us say k psi I, into a continuum of final state k psi f. Actually, this final state is just continuous state. And for this, let us consider that this rho of EF is the density of final states. When you say density of a state, what does it mean? It is the number of quantum states in unit range of energy. You have been encountered with such a density of a state at several places in my previous videos, okay, in statistical mechanics, in quantum mechanics, everywhere. So when you say that rho of EF is density of the final state, it means what? It means the number of states per unit energy interval. Okay, in unit energy interval, the number of states is equal to rho of EF. Okay, because we are talking about the final state, so rho have been written rho of EF. Okay, as our aim is to find the total transition rate. So first of all, we will talk about the transition rate for a small energy interval. Let us consider that the energy of the final state lies between EF and EF plus DEF, where DEF, you know, is the energy interval which is very small. Now, since EF and EF plus DEF are very close to one another, because we consider that this DEF is very small. So, with this slight change in energy, there will be no appreciable change in the value of density of a state rho of EF. So, you can consider that when the energy of the system in final state is EF, then its density of a state is rho of EF. And when its energy becomes EF plus DEF, even then the density of a state is rho of EF, because this DEF is not very large, it is very small, negligibly small. Now, in accordance with definition, for unit energy interval, the number of states in number of final states is rho EF for unit energy interval. So, what will be the number of final states for the energy interval DEF? That will be simply rho of EF times DEF. Okay, it is just by unitary method. So I have mentioned here the number of final states within the energy interval between EF and EF plus DF is simply equal to this much. Okay. Now, if your aim is to find the total transition rate, how you will obtain? You will simply integrate this result for the entire range of energy, and then we will get the total transition rate. So if you denote the total transition rate by the symbol WIF, then this will be integral of this gamma IF times this much. Okay, this is the number of states, and gamma IF, you know, this is the transition rate at the energy EF. So when this will be integrated for entire range of energy EF, then you will get the total transition rate. Now let us substitute the value of this gamma IF, which you have defined in this equation 4. You can see this is the expression for gamma IF. We will substitute it in that very equation and obtain the value of WIF, which is actually called the total transition rate. Okay, so let us see WIF. When you will integrate it, you can see this is a constant factor after using equation 4, and inside the integral there will be rho of EF times delta of EF minus EI DEF. Now here, you know, a very important property of Dirac delta function is if you find the integral of product of a function, continuous function f of x with delta of x minus x naught, delta of x minus x naught. Then what is this? If you will study the property of Dirac delta function for all space, here for entire range of x, this integral will be evaluated. Then it is found that this is simply equal to f of x naught, that is value of f at x equal to x naught. So utilizing this very important property of Dirac delta function, you can see the integral of rho of EF times delta EF minus EI will be what? Here there should be dx. This will be simply rho of EI. Okay. At the place of x naught, here there is EI, and at the place of EF there is x. You can see. So the total transition rate WIF, this is equal to what? 2 pi over h bar times a square of the modulus of this very quantity, which is actually the scalar product of V hat operated on psi I with psi f. Okay, and as I have told you, all these important results you must remember for solving the problems and also for seeing the different applications. Okay, so you must remember it. Okay, this result which we have obtained here in this equation number 6, this is the result which is known as Fermi golden rule. So if you have been asked in your examination to write a short notes on Fermi golden rule, then what will be your starting point for your answer? You have to start from here. Don't write this heading, okay? uh, you have to start from here, and you have to mention the expression for this gamma if which I have obtained earlier. So remember the expression for gamma if, okay, and then find this expression, and that will be a good answer for your question, okay. So this result, final result, you can see here. This is called Fermi golden rule. Actually, what this Fermi golden rule implies, okay? In fact, it implies that in the case of constant perturbation, if we wait long enough, it means if you are talking about a time which tends to infinity, the total transition rate, that is WIF, becomes constant, that is time independent. You can see in the RHS of this expression, there is nothing which will vary with time. So this is a very remarkable fact, that the total rate of transition becomes constant, it becomes independent of time. But when? After a long time. So after a long time, there will be just a saturation state when the transition rate will not increase, okay. And this result is actually called Fermi golden rule, okay. So in this way, we have completed the concept of constant perturbation, okay, for finding that transition probability for constant perturbation. Now, as I have told you that in next subsequent lecture, we will see another very important calculation, and that will be regarding the transition probability for a harmonic perturbation or periodic perturbation. I have seen in some of the university examination, an independent full length question is asked regarding this uh, harmonic perturbation, okay, and that you will find in my next lecture, okay. Thank you very much.